We're going to talk about how to make your blockchain and regular apps quantum resistant. And you might wonder how we got to this topic. Well, ING is very active in both spaces, in the blockchain space and quantum computing space. For instance, one of our researchers, Adil Akun, he does a lot of research work. He has a PhD in quantum computing. He works on modeling investment portfolios using quantum computers because it's a multi-variable, multi-state problem, which is best mapped to quantum computers. Adil Akun is very focused on using the benefits of quantum computers. But as you might know, quantum computers can also threat the current cryptography, and which is why we, Dapeng and I, from the blockchain team, also focus on the impact of quantum computers on cryptography. Dapeng has a background in quantum computers, experienced in using D-Wave at Volkswagen Group. And myself, I have a long background in blockchain technology. So that's how we got together, and how we decided to modify blockchain technology to make it quantum resistant. So if you look at what ING does with blockchain technology, you see that we build applications using blockchain technology, obviously. For instance, things like HQLAX, it's a separate fintech where ING supported the initial versions of the technology stack. Also, we improve blockchains to make the transactions more confidential. That's our work with the ZK crypto GitHub repository. You can find it. It's open source. So yeah, basically we not just use the technology, but we also like to improve it. So without further ado, what is quantum computing? And I would also like to cover where we are today, because when Dapeng and I were planning our trip to London, we were actually at a certain point. I was a bit concerned. I was a bit afraid. I said we were entering all our data in this booking system, and I said to Dapeng, is it really safe what we're doing? I mean, there's this padlock, it says HTTPS, that uses TLS. Is that still safe? I mean, there's so much going on in this quantum computing space. Google has reached quantum supremacy with a 56 qubits machine. There's IBM, who plans to have a 1 million qubit machine in the coming 3 to 4 years. There's a lot of different parties working on quantum computing, including Intel, Microsoft, Google and IBM, D-Wave, etc. Many parties. There's a lot going on. Is it still safe to use this crypto? So let's see where we are, what quantum computing is, where we are today, and how it will impact us today and in the future. First of all, what is quantum computing? So quantum computers, they use quantum physics to store data and perform computations on it. And where a classical computer with a binary bit can be either 0 or 1, qubits can be in a superpositioned state where they are 0 and 1 at the same time. Which is why if you want to do a certain calculation, you need less qubits for the same calculation as you would with classical bits. Or if you turn it around, if you have the same number of qubits as you would have as compared to classical bits, then you have a much more powerful computer. Quantum computers, they use superposition, so qubits can be 0 and 1 at the same time, and they use entanglement. So 2 qubits can be in exactly the same state, even if they're otherwise disconnected and in a different location. These are 2 quantum mechanics properties that are used by quantum computers. A specific type of quantum computers is quantum annealing. For instance, D-Wave, they're very big in quantum annealers, and they can solve specific problems like sampling and optimization. And this contrasts to gated quantum computers, like the ones made by IBM and Google and others, which can solve any problem. Quantum annealers typically have more qubits. I think the current state of the art with D-Wave is 5,000 qubits. Current state of the art for gated quantum computers is 128 qubits. However, because they can only solve the quantum annealers can only solve specific problems, they cannot be used to break the current cryptography. You need gated quantum computers for that. Also, quantum annealing uses quantum mechanics. So they use superposition and entanglement, and they try to find, or they will find the minimum energy state of the qubits to optimize logistical problems. So you can model logistical problems using the qubits, and then because it uses the lowest energy state, you are guaranteed to find the optimum, for instance, for a logistic problem. If there are several optimums, local optimums as we call it, you are guaranteed to find the global optimum. So really the best logistic solution, the best solution to your logistics problem. So with all these headlines, IBM planning to do a 1,000 plus qubit quantum computer, even they're preparing this super refrigerator for a 1 million qubit quantum computer, Google achieving quantum supremacy, etc. Where are we today? Well, let me start with the reassuring fact that all the quantum computers that we know today are cryptographically irrelevant. So yes, you can factor small numbers into the prime factors. The number 15 can be factored into 3 and 5, and number 21 can be factored in its primes. But larger numbers cannot be factored by the quantum computers that we have today. So we have small laboratory scale gated quantum computers that have been built. Google's quantum computer is supreme in solving only a theoretical problem. And with supreme, we mean that for this specific theoretical problem, the Google's quantum computer is faster than any classical computer known and available. I think they compared it to the NASA supercomputers provided by IBM, so traditional classical computers. And the larger systems, the quantum annealers, they can address some type of computations, logistics, but they cannot attack the real world cryptography. So today, all the known quantum computers are not cryptographically irrelevant. So today, we should be safe. However, you see that the number of qubits is rising fast, and this dotted line, that's where we are roughly today. What everything right from the dotted line, that's projections. IBM plans for this year, 2022, to have a 433 qubit machine. And for the year after, 2023, they plan to have 1,000 plus qubit machine. And a couple of years after, they plan this 1 million qubit machine. So even though today all the quantum computers that we know are cryptographically irrelevant, we also know that you could argue that Moore's law, whether or not Moore's law applies here, but you see that the growth in number of qubits is rising exponentially. That's why we should buckle up and prepare today. We should learn today what is required to make our cryptography quantum resistant. Because not only at a certain point, quantum computers will become cryptographically relevant, and they will be able to break today's crypto. And as soon as that's done, we will need some time to change our systems, depending on how efficient you are, etc. That will have some lead time. But also, if your traffic, for instance, your TLS encrypted traffic is recorded today by internet service providers or whatever, it's recorded today, even though today it might not be broken. As soon as there is quantum supremacy with regards to cryptography, then they can still, in the future, read what you have done today. And depending on the type of information that you're sharing, that could be an issue. So what do I mean specifically with the impact on cryptography? So what's the impact on cryptography? What does that mean specifically? Well, first of all, if we look at cryptographic hashes, Grover's algorithm basically reduces the safety of hash algorithms by half. So if you have a SHA-256 hashing algorithm today, it will be as safe as a SHA-128, so half as safe when quantum computers are out there. So the fix against this is simple. You can just double the size of your hash. So if you use SHA-256 today, you can upgrade to SHA-512 in the future. Symmetric encryption. For symmetric encryption, which is also affected by Grover's algorithm, you could say that also doubling your key size will still keep it safe. You see that, for instance, AES-128 could be broken with 3,000 logical qubits. AES-256 would need 6,500. So doubling your or increasing your key size will give you protection for symmetric encryption. You should be reasonably safe to keep up here. However, with asymmetric encryption or public key encryption, Shor's algorithm will affect that. It basically means all the asymmetric encryption that we know today can be broken with twice as many qubits as the key size. For instance, for RSA, a 2048-bit RSA key would require 4,096 qubit quantum computer. For digital signatures, the current popular ones like ECCC and RSA are broken. For RSA, a signature with a 2048-bit key, you need a 4,096 qubits computer. If you compare that, if you look at RSA and elliptic curve cryptography, they rely on very different cryptographic assumptions, where RSA uses prime and modular integers, and elliptic curve cryptography uses discrete logarithm. then you see that per horizontal line in this matrix, RSA has roughly the same safety as the ECC equivalent. So you see that, for instance, on the top line, a 1024 bit RSA key has roughly the same safety as an elliptic curve key of 163. That is today. However, you see that the effects of the number of qubits required to break it, you see you need much more qubits to break RSA than to break elliptic curve cryptography. And that's because of the underlying cryptographic mechanisms or cryptographic assumptions which are different for RSA and elliptic curve cryptography. So basically, as the number of qubits go up, in theory, you could keep up by increasing the key sizes, but at a certain point that would become impractical, which is why there are different cryptographic schemes with different underlying mathematical assumptions in order to protect against quantum computers. But before we look at that, first let's see at how all this crypto affects blockchains. So you see, for instance, SHA-256 hashing, which is broken by Grover, that's used by Bitcoin, Ethereum, Dash, Monero, basically all the big ones. And you see, same for ECDSA, Qcon hashing, etc. They're all affected, so they should be swapped out. In summary, the impact on blockchain and distributed ledger technology. Digital signatures, every transaction, every update you send to a blockchain is digitally signed. They should change to have a post-quantum signature scheme. The hashes should be doubled. The size of the hashes should be doubled. Proof of work, which relies on reversing hashes, obviously that is affected. You could argue that with a quantum computer, the hashes can be reversed faster. That doesn't mean that the block frequency would go up. It simply would mean that the difficulty of the blockchain would go up. Right? That's built in the mining protocol, that the block frequency always remains constant. So if for some reason new blocks are found faster, whether that is just regular classical computing power being added to the network, big mining farms joining the network, or whether that is due to quantum computers, in the end, the block frequency will remain constant. So if the blocks are found faster, then the difficulty goes up to offset that effect, so that the frequency stays stable. Zero knowledge proofs, it depends. A popular zero knowledge proof scheme is ZK snarks. Also, they are affected by quantum computers, meaning that the information on which the proof is based will still remain confident. However, false proofs could be generated with quantum computers. So that's basically no longer usable. Then so far we talked about quantum computing. There are also other applications of quantum mechanics, for instance, quantum random number generators or quantum key distributions. They could also obviously impact blockchain technology. Then how to solve this? There are many different ways to make post-quantum crypto, quantum resistance crypto. For instance, lattice-based, code-based, multivariate polynomial cryptography, or hash-based signatures, even many others. There are many schemes out there. There's no standard way of doing that. Dapeng will elaborate on that. There's a standardization process going on. For whatever currently available post-quantum crypto scheme you choose today, it will impact your performance. It will be slower to sign, slower to verify the signature, but the signature size will also increase. And that's, for instance, what you see with TLS. TLS uses a combination of digital signatures. The certificate is signed, for instance, which should be verified. It uses asymmetric encryption during the handshake, symmetric encryption during the remainder of the TLS session. Well, the symmetric encryption we just saw a few slides back, that should remain safe. Only you should increase the key size. But what's the point in that if the key is leaked during the handshake? Because the handshake uses asymmetric encryption. So in order to make TLS safe, the signatures should change, but also the asymmetric encryption. There are ways to do it. There's no standard yet. There's the NIST competition is going on. All of them will affect the handshake time, the TLS handshake time, because it's longer to verify, larger packages, etc., etc. And that's exactly what we saw in practice, because Google, they actually provided post-quantum cryptography in Chrome, in one of the Chrome versions. And basically they had to revert that update. They had to disable it because the internet providers basically had TLS timeouts. TLS handshake has a timeout, and there's a good reason for that. If the timeout is too long, you could have a DOS on your handshake only. So there's a reason why timeouts currently are short, but they should become longer to support post-quantum crypto. So that's you cannot just say post-quantum crypto, you know what, it's a bit slower and sizes are longer, so I'm just going to need more disk space or more computers or something like that. It's not that simple. There's a reason why timeouts are defined. Right? It's a safety feature. So this is really something, a tough nut to crack. However, the optimistic point here is that also post-quantum crypto, there's a lot of development going on, and those schemes are also becoming more efficient, which is what why Dapeng and his team, they chose a very efficient signature scheme to implement in Corda, but more on that later. So what is Corda? Corda is the DLT that we use a lot in ING and in the financial world. It's developed by R3, a big consortium with hundreds of the world's largest financial institutions. They created Corda distributed ledger technology inspired by blockchain technology. Though strictly speaking, the transactions are not yet are not batched in blocks. So strictly speaking, it's not a blockchain, but that's an implementation detail. It does provide the same advantages or similar advantages as blockchain technology, such as a consistent, trusted view on shared data, which can drastically improve the cooperation between different companies. Currently, often when you have interfaces with other companies, you have a shadow bookkeeping to see if at the end of the day you compare your end of day statements. You compare like do we still have the same view on which messages we exchange, etc. That obviously is not required with blockchain and also not with distributed ledger technologies such as Corda. Corda also uses enterprise grade technologies, enterprise standard technologies such as Java Virtual Machine or AMQP messaging and other. So it also integrates well in large enterprises. Corda is specific for networks with known and identified participants. So it's not meant as an open network such as Bitcoin and Ethereum, where anybody in the world can just anonymously deploy smart contracts and trade cryptos, etc. It is designed to work as a permissioned ledger. So how does ING use Corda? For instance, we've built HQLEX, or we've built the initial versions of it. It's now a separate company. We are involved in Contour for trade finance, but we also improve Corda. So we improve the privacy while embedding zero-knowledge proofs, but we also improved it by making it quantum resistant by plugging in a very efficient signature scheme. Dapeng, you take it from here.
Thanks, Cees, for the introduction. I will continue with the NIST contest and the candidates. NIST is the National Institute of Standards and Technology in the US. It has been a long time for the cryptography community study crypto algorithms that can resist quantum computer attacks. It can be traced back to MC Alice encryption and Merkle hash signatures in the 1970s. And the importance of post-quantum cryptography has gradually emerged in the past decades. There are many important participants involved in the research and standards of post-quantum cryptography. In addition to NIST, there are European Union PQC project, European Telecommunications Standards Institute, and so on. In our project, we selected the PQC algorithm from NIST candidates. And NIST started the research work on post-quantum cryptography as early as 2012. And launched a global collection of post-quantum cryptography standards in 2016. And NIST mainly focuses on the collection of the following three types of post-quantum crypto algorithms: the encryption, key exchange, and the digital signature. Until now, NIST has received a total of 82 draft algorithms and published 69 finalists. The 69 finalists mainly include post-quantum crypto algorithms constructed by the following four mathematical methods, as Cees mentioned in the previous slides: the lattice-based, code-based, multivariate-based, and the hash-based algorithms. If you are interested in the PQC algorithm and the implementation, I would like to introduce you an open source project, the Open Quantum Safe. This is an open source project that aims to support development and the protect of quantum resistant cryptography. Below this page is their official website. And Open Quantum Safe provides two main work, the libOQS and OpenSSL library. libOQS is an open source C library for post-quantum crypto algorithms, providing key encapsulation mechanism, signature schemes, and the open API. That means libOQS can be used with different wrapper in Python, in Java, in Go, and across different operation systems. This is quite handy to embed PQC algorithms from NIST, such as the NIST Round 3 finalists. We have the test-based PQC algorithm, Dilithium and Falcon, the multivariate-based PQC algorithm, Rainbow. And based on the researches in the recent years, the test-based PQC algorithm is considered to be the most promising post-quantum cryptography technology. Falcon and Dilithium are both lattice-based PQC algorithm, but we go for Dilithium. We choose Dilithium because it is a lattice-based signature scheme. Dilithium has strong security under selective message attacks, with the smallest public key size, signature size, fast speed, and low memory usage among the PQC algorithms. We also have the benchmarking as reference to show you how outstanding Dilithium is. This is the benchmark on memory. Among these 5 PQC algorithms from NIST candidates, For the memory, it should be the smaller the better. From this comparison, Dilithium, Falcon, and Sphinx Plus have low memory usage, and Rainbow, Picnic cost much more communication resources. So at this stage, Dilithium, Falcon, and Sphinx Plus stand out. From the memory benchmark, we knocked out Rainbow and Picnic. Here we come to the key size and signature size. This performance should be the smaller the better. We can see that Sphinx Plus has bigger signature size than Dilithium and Falcon. And at the same time, Dilithium and Falcon have smaller key size and signature size. So after this round, we only have Dilithium and Falcon left. And the last comparison is the speed. Speed means the quicker the better. If we map this concept to the graph, it means the bigger the better. We can find the Dilithium is quicker than Falcon, not only in the key generation process, but also in the signing and verifying process. So until now, we've already selected the best PQC algorithm from NIST candidate. It is Dilithium, which has small public key size, fast calculation speed, and low communication cost. Okay, let's talk about how to make Corda quantum safe with Dilithium. As I introduced Open Quantum Safe just now, it provides a library called libOQS. If we want to connect libOQS directly to Corda, we cannot make it. But still remember, libOQS provides all kinds of wrapper. Assume here, we use the Java wrapper. But even if we have the Java wrapper, we still cannot make it because the security standard of libOQS does not match Java security standards. But nothing can stop us. We followed the Java security standards and made a provider called Open Quantum Safe Provider. It can integrate the PQC algorithm into Corda with the help from libOQS Java wrapper. The Java security provider we implemented, it is a library with implementations of various crypto primitives following the predefined standards. But what else makes this library so cool? First, it is written in Kotlin. Maybe you don't know about it, but for Corda, it is an advantage unless you want to plug it into JVM itself. So it is pluggable. And in a sense, if you want to write your own application using PQC algorithm, you can just add a dependency and write one line of code in your application. And finally, it just conforms to existing standards of regulations. So you don't need to worry about transformation logic. So under these kinds of protection, user can safely generate certificates, sign new messages, verify them, and all of this is done using Dilithium, which is quantum resistant and quite effective. And we prepared a demo to show you the functionalities about our service.
Let's have a look at the example that we prepared. And our network consists of notary node and two actual nodes, party A and party B. This is a very simple example. These nodes just send information about lenders, borrowers, and borrowed value. And each time, nodes send transaction details, which you can see on the screen. You need to gather signature of counterparties, and it needs to verify transaction every time when it receives transaction details. In order to do so, nodes need to use private and public keys, which are processed in dedicated key store. In our case, we need to contain them in the node key store, which is the default location in Corda. Okay, I have already opened it, and as you can see, we have identity private key entity, and here we have subject public key algorithm. It is an object identifier of Dilithium algorithm. And since we have it already, we can start to try to perform some transactions. For instance, repeat the transaction we had before. And here we say that party A, the party A, also party B, the 50 units. And if we do so, you see it generates transaction, then it verifies contract constraints, which is relevant to our point, and it signs transaction, gathers the counterparty's signature, collects signatures, and verify them. So if we have a look at here, we notice that it did verification 2 times using the lithium algorithm, and then it signs and verifies twice. It happens because firstly, you need to create signature that to be verified, and you need to send it. The thing is that it verifies in the end once it receives transaction, which is signed using the lithium algorithm.
And so the future plans, we are going to clean up the code and make it as open source, and ideally including our features into Corda as an option when our implementation is mature enough. So yeah, that's all about our presentation. Thanks for your listening, and if you have any questions, please just let us know.